Our next section is 5.2, Spectrum and Dynamical Systems. Maybe in some other courses like control theory or fluid dynamics, you've already seen dynamical systems, and if you did so, then you've already learned that the spectrum is a very important tool in understanding these systems. And we will just recall only a little bit of that here. And let's do that for a very simple example. Let's take a population model. And let's suppose you have decided to breed sheep. So you go to the most famous sheep person of your country and buy 2 lovely sheep, which are still very young. And the sheep person tells you that your lovely baby sheep will grow up within a year or so. And then when your sheep are grown up with a certain probability, let's say beta equals 25%, they will give birth to another pair of baby sheep. And the third message before you leave the sheep guy is that, of course, sometimes your sheep die. And currently the percentage is about 20% of your population die within a year. So you conclude that 80% survive. Okay, and then you go home, and on your way home you start thinking, will I be successful? Will my herd of sheep grow and eventually cover the whole country? Or will it grow for a little bit and then eventually die? Or will it just stabilize at some nice level of 10 or 20 sheep or so? What's going to happen? And of course you could just wait 10 years, 20 years, 100 years. But if you don't want to wait, then you need mathematics and you need dynamical systems. And let's look at the number of adults and the number of babies at year number k. Okay, and then as 1 year goes by, here's your new population vector of adults and babies at year k plus 1. And I mean, based on the knowledge that we have about births and survivals, we can just compute the average or the expectation values for the new population counts. I mean, if your adults didn't die, then you will keep them, and the ones that were babies the year before are now also adults. So that would be your new number of adults in year k plus 1 if no one died. But now you have to multiply that by 80% because 20% will die. Okay, and how many babies are you going to have next year? Well, every pair of adults that you had this year with a percentage of 25% is going to have a new baby. Okay, and that's your population vector at year k plus 1. Now let's try to express that in terms of the population vector at year k. And looking at these entries, you obviously need the following matrix. Here you want sigma times ak and sigma times bk, which gives you sigma here and here. And here you want beta times ak, which gives you a beta in the first position here, and that leaves the last position empty. Okay, so that's your matrix that lets your population age by 1 year. So instead of having to wait for a year, you could just multiply your population vector by that matrix. And instead of waiting 10, 20, or 100 years, you just multiply 10, 20, or 100 times by that matrix A. And in your linear algebra course, you have learned that powers of A are best computed via a diagonalization of A. Okay, and hoping that your matrix A is diagonalizable, you write it as a product of a matrix that carries your eigenvectors, and then comes a diagonal matrix with your eigenvalues, and then the inverse of that first matrix again. Let's just abbreviate this by matrix X times matrix D times matrix X inverse. And if you do that, then a to the power n means you have to write the product xd x inverse n times, one after the other. But then obviously you get cancellations whenever x and x inverse meet, which happens here, and it's going to happen here and here and here. So all the x's and x inverses except the very first and the very last go away, and all you're left with is x and then d to the power of n, and at the very end you will have x inverse. Okay, now this shows you the obvious benefit of that attempt, because it's a lot easier to take a diagonal matrix to the power 100 rather than taking that matrix to the power of 100. Okay, now we can substitute back what our matrix D is, and we see that the nth power of that diagonal matrix is just taken by taking the nth powers of the corresponding diagonal entries. So just powers of numbers. Okay, and now if you want to know whether your career as a shepherd is going to be a big success, you just have to look at these numbers here. Are they growing? Are they going to zero? Are they remaining at some stable level? And that's of course not difficult, because which complex numbers will grow if you take them to the nth powers? Well, the ones that have modulus bigger than 1. Which ones go to 0? Well, the ones that have modulus less than 1. And which ones stay at the same size? The ones that have modulus equal to 1. Okay, so you see that your sheep population grows unboundedly if one of your eigenvalues has modulus bigger than 1. It goes to 0, poor sheep, if both your eigenvalues have modulus less than 1, and it remains at about the same size if one of the eigenvalues has modulus 1 and the other less than or equal to 1. And we can express that nice and short by saying that the maximum of the moduli of my two eigenvalues is equal to 1. In fact, we can also express the other two cases in terms of that maximum, so let's give that maximum a separate name. And let's call it R, or even R of A, because it depends on the matrix A, because these are the eigenvalues of A. Then we could say in the first case, instead of saying either the first is bigger than 1 or the second is bigger than 1, we could just say the larger of the two is bigger than 1. Then in the second case, instead of saying they are both smaller than 1, we could just say if the larger of the two is smaller than 1. Okay, and the third case is already expressed in terms of our maximum. So we can drop that previous bit here. So more generally, not just for 2x2 matrices A, but for general matrices or operators from a space X to X, call the largest of the modulus of the moduli of your spectral values the spectral radius of A. So for all points in your spectrum, you're checking how far is it away from the origin, and the longest of these lines is what you call the spectral radius. And you call it spectral radius because it's the radius of the smallest disk around the origin that covers the spectrum. And we know from our lemma 1 that norm of A is enough to do this job, but possibly the spectral radius is less than or equal to, or is maybe less than the norm of A, and we will investigate that in the next section. But before we do so, let's do something else. So coming back to our sheep breeding activity, we're going to be very successful if the spectral radius of that matrix A here turns out to be bigger than 1. we're going to be moderately successful in the sense that our population is staying at some roughly fixed size if the spectral radius of that matrix A here is exactly 1. And we're going to be very unfortunate in the sense that soon all the animals will be dead if spectral radius is less than 1. Well, in our particular case here, where we chose beta and delta, or beta and sigma, to be 25% and 80%, our two eigenvalues turn out to be 1 and minus 0.2. So the spectral radius, the modulus of the larger, is 1. So this means we are moderately successful. So the size of our population is going to stabilize at some point and not grow and not fall from there very much. But of course, if you improve the living conditions by, I don't know, getting better food or playing with your sheep daily, then you might improve birth rate, or you might improve the survival rate, and then you're very close to being extremely successful, because you're getting your spectral radius above 1